Today I want to talk a little bit about a model that we use to describe the shape of molecules. So we're going to be talking about molecular geometry, so the shape of molecular compounds. And recall that molecular compounds are ones that are made up of nonmetals with other nonmetals, and the atoms are bonded together with covalent bonds, meaning they're sharing their valence electrons. So the model that we use to describe the geometry of these is called VSEPR, and it stands for Valence Shell Electron Pair Repulsion. And I like to say that if you know the name of it, if you know what the acronym stands for, then you can tell me about the model because it's all right there in the name. But before I get into the details of that, I want to make the distinction between molecular geometry and VSEPR geometry because they are related and they are often confused for each other. But in this video and in future videos, I'm going to be making the distinction between the two. So I want to make sure that that's pretty clear in this kind of introduction to the model. So molecular geometry, as it sort of sounds, is the shape of molecules. So it's the geometry of the molecule based on where the atoms are located. So thinking about the atomic nuclei, if we picture a Lewis dot structure, the first thing we do is we take a central atom and we put these outer atoms around it, and where these outer atoms' nuclei are, kind of in three-dimensional space, is the molecular geometry. So it's the shape of the molecule. Now the VSEPR geometry, or the electron pair geometry as it's sometimes known, is the shape of a molecule that's based on more than just where the atomic nuclei are, but based on where the electron pairs are. And so I'd like to define electron pairs here as not only the covalent bonds, because they are, so atoms that are covalently bonded to a central atom, and these could be single, double, or triple bonds. So they could have a bond order of 1, 2, or 3. It doesn't matter how many electrons are being shared between the atoms, we still count that as one electron pair. And again, that's kind of a weird distinction. We'll get into the details of that in a future video. Or, so that's kind of option one, or they could be a lone pair of electrons. And recall that lone pairs of electrons are those non-bonding pairs. So electrons like to be in pairs. One is spin up and one is spin down. And these pairs then can be shared between atoms, giving you a covalent bond that has those atoms kind of stick together. Or it can be a lone pair of electrons, which is just a pair of electrons that's going to take up some amount of space. So these electron pairs in a VSEPR context can be either or. So the distinction then between molecular geometry and VSEPR geometry is that the lone pairs are factored in for the VSEPR geometry. That's the only difference, right? It's the shape, but we're factoring in these lone pairs as well as the atoms that are covalently bonded. So let's look at the rest of it, because like I said, if you know the acronym, then you know the model. So if we say valence shell, as a reminder, valence shell is the outermost shell on an atom, and remember that a shell, if we kind of think of the Bohr model of the atom, represents energy. So the outermost shell, for the electrons, it has the highest energy. It's the furthest away from the nucleus, so we have the greatest potential energy. And then this EP part is the electron pair part. And so the electron pair can be either the covalent bonds, electron pair, or it can be the lone pairs of electrons. And then the last bit is repulsion. And if we think about this from just a purely physical standpoint, if I have negatively charged particles in close proximity to each other, then kind of like the same end of a magnet, if I have two negative poles of a magnet and I try to push them together, their natural inclination is going to be to repel. So that's the same kind of thing with electron pairs. If we have a bunch of negatively charged particles in close proximity to each other, they're going to repel each other and move around the central atom in such a way to where they're going to give themselves as much space as possible. So what VSEPR says is that electron pairs will spread out as much as physically possible around a central atom. And we're going to get into nitty-gritty details on this in future videos, but I just want to talk in this particular one about kind of an overview of this model and kind of the thinking, because spatial reasoning and thinking in 3 dimensions is something that students sometimes struggle with. I know that when I first was learning general chemistry, I definitely struggled with my kind of 3-dimensional spatial sense, and that's something that you get better at when you study chemistry, which is kind of exciting. I think it's exciting. Okay, so VSEPR says that electron pairs are going to want to spread out around a central atom as much as physical space will allow, and that's because these negatively charged electron pairs are repelling each other. So these outermost electrons, which are the highest energy, are in pairs, either in forms of covalent bonds or lone pairs, and they're repelling each other so that they spread out as much as physically possible. And there's kind of VSEPR in a nutshell. So let's talk about what this actually looks like in some sort of real context. Realish context. I'll give you some actual examples in future videos, but let's at least talk about it from a geometric standpoint. So if I have 2 pairs around a central atom, so my central atom here is this kind of tan orangey one. If I have 2 things around it, the furthest apart they can get is the opposite ends, right? They are completely as spread out as physically possible. And if I look at this thing in 3 dimensions, right, I can see if I'm looking just straight down it, it's a straight line. All of these guys are on the same line. I have 3 points on the same line. We call that geometry linear. You know, it's not really, chemists aren't necessarily known for their creativity in terms of naming things. And if we think about the angle that is between these 2 electron pairs, then it's 2 90-degree angles. So it would be 180 degrees from one to another. And again, that's linear geometry. So 2 things around a central atom, in order to spread out as much as physically possible, they're going to go on opposite ends. Now, if we apply the same logic to 3 pairs, we have 3 electron pairs around a central atom. They're going to spread out as much as physically possible. Then we get this kind of like fidget spinner looking kind of molecule. I think it looks like a Mercedes-Benz symbol. Not that I've ever had a Mercedes-Benz, but if you put a circle around it, you can kind of picture it as a hood ornament in my mind. So if I have 3 pairs, and I wanted to spread out those pairs as much as physically possible, we can see, if we're kind of looking straight down the axis here, that these things are all in the same plane. So trigonal, meaning that there's 3 things. Plane, meaning that they are, you know, planar, that all of the atoms, if I was to slice through this thing with a piece of paper, all of the atoms would be on that piece of paper. So we call this geometry trigonal planar, or we would say that this shape is a trigonal plane. Now, in terms of internal angles, so thinking about the angles between these different pairs, if I was to put a circle around this, we know that a circle is 360 degrees. If I was to cut it into 3 parts, then each of these angles would be equivalent to each other, and they would all be 120 degrees. And you can kind of see that if you have some geometric sense of kind of angles. If you're picturing a 90 here and a little bit more, kind of gives you your 120. So that's this trigonal planar geometry. Now, if we increase the number of pairs that we have and go to 4 pairs, that gives us what is called tetrahedral geometry. Now, tetra as a prefix means 4, like tetrapod, or when we were talking about naming in past videos, we talked about 4 of a thing having the prefix of tetra. And when we're talking about it in this context, of course, we're talking about 4 electron pairs around a central atom. So we say that the geometry is tetrahedral, and the shape that forms is a tetrahedron. So you'll see these kind of interchangeably used for 4 pairs around a central atom. Now, I want to talk a little bit about the conventions that we use on a 2-dimensional surface and relate that to the 3-dimensional object. So we have 4 things around a central atom. So I'm going to kind of rotate that around so you can kind of see visually that each of these things are as spread out as possible. So we have all these equivalent internal angles between the electron pairs. And when I'm representing this on a 2-dimensional surface, I have these lines here that look like normal lines, kind of like my lines on my trigonal plane. That means that the lines here are in the plane of the surface that I'm writing on. So these would be flat to the surface. With my trigonal plane, remember the whole thing is flat, so the way that I've drawn it is flat to the surface that I'm drawing on. I could draw it like this. You know, I could draw it like this, I could draw it like anything, but it's easiest to draw when it's flat to the plane of the surface that we're drawing on. So if we're thinking about these two, then that's, let me get that here kind of oriented. Perfect. Okay, so that's this one and this one. And if I was to slice through these would all be in the same plane, and you can kind of see that if we look straight down on it. These guys are in the same plane. So I'm drawing them as if these guys are in the plane of my paper, right? So this is flat to my paper. And if I look at the other ones then, if these guys are flat, this one is sticking out at you, and this one is sticking back into the plane that I'm drawing on, because here would be my surface of my page, right? So this one's coming out at you, this one's going back into the page. So the way that we would draw that on a two-dimensional surface, because we're sort of limited by that when we're representing them, is by this blocky triangle. So this triangle that's filled in that gets bigger as it comes out at you, right? So it's coming out at you in 3D. And so that represents this guy that's coming out of the plane at you. So this guy is this guy. So it's a filled in triangle, and you have kind of the base of the triangle that's coming out at you. It gets smaller as it goes back into the central atom. It gets smaller as it goes back into the central atom there. And then if we think about the opposite then, if we start small here, kind of, or start larger here because it's closer to us, and get small towards the end, then that's what we have with this back one. So this back one that's going into the plane, sorry, shaky. This one that's going back into the plane is this hashed or kind of shaded, or however you want to think about that, triangle. So it's kind of a, I think about it as a triangle that's made out of a bunch of lines, you know, so kind of a hash mark triangle that gets smaller. So we go away, and that represents this guy. All right, so that was a kind of overly lengthy explanation for no reason, but if we think about each of these angles, then they're all equivalent to each other. So each of these internal angles is equal, and then they're equal to 109.5 degrees. That's the geometry that works for a tetrahedron. Now, tetrahedrons in general are four-sided pyramids. If I was to draw in lines that connected all these, we could see there's kind of a plane here, a plane here, a plane here, and a plane on the surface it's sitting. So we'd have kind of a four-sided triangle, triangular pyramid or a tetrahedron. Okay, now 2, 3, and 4 are kind of the most common when we're thinking about molecular geometries, but there are some molecules that break the pattern. They break the octet rule, and so you can sometimes have 5 pairs around a central atom, and that looks something like this. If we do some rotation here, we can see that there's kind of 2 sets of atoms. There's this sort of set here that looks like a trigonal plane, and this set here that's a straight line. So we have kind of a line with a trigonal plane that is coming through it, and that's our trigonal bipyramid, or we say that it has trigonal bipyramidal geometry. So there's kind of 2 different sets of atoms here. There's this equatorial set, you know, meaning that it's on the equator of the molecule. So if we're thinking about that here, that's these guys that are the trigonal plane. And then we have what are called the axial atoms, which makes sense because they're along the axis. So that's the one that's kind of linear. So we have a straight line here with our trigonal plane that cuts through it. So we have 2 different types of angles here. We have a 90-degree angle, and then we have the 120 degrees in the equatorial position. Now, if we go to 6 pairs, then we end up with octahedral geometry, where we have kind of a, I think it looks like a jack. So we have a central atom with 6 things around it, and we have all 90-degree angles. So everything internal here is 90 degrees, and you can kind of see that with this guy. So we'll look at some examples of these in future videos. I just wanted to give you a sense of what they look like, kind of a smaller context with just the model in mind, and I will talk to you again soon.